Hey guys, so today let's talk about covalent bond formation. So first we need to know two basic theories that help us explain covalent bond formation. The first one is the valence bond theory. The valence bond theory says that if an electron spins are paired, the covalent bond between two atoms is the overlap of the atomic orbitals. For example, if I have, say, a hydrogen atom here and another hydrogen, the two will combine to produce an overlap and produce this hydrogen molecule H2. The second theory is the molecular orbital theory. It states two things. A, molecules are in a way like an atom, and two, it has orbitals of distinct energy levels, like s, p, d, and f orbitals. Here, again, is the example of hydrogen atoms forming hydrogen gas. Now, we can see both of these theories in action here. As mentioned earlier, we can see the two hydrogen orbitals, here and here, merging together to produce a molecular orbital of hydrogen gas. We can also see that these orbitals are also s orbitals, and this orbital is also therefore an s orbital electron pair. And there are two major types of bonds that can be found in covalent bonds. Sigma is the first one. A sigma bond is basically an S and S bond, an S and P bond, or a P and P bond. For example, two s orbitals can intersect to produce this hydrogen gas molecule, for example. Or an s and a p orbital can merge together to produce this molecule, which has an s and p bond, but it's also a sigma bond. And lastly, the two p orbitals can merge together to produce a molecule, which again is a sigma bond. The second one is the pi bond. Now pi, unlike the food or the number, in chemistry a pi bond is this sideways overlap of two p orbitals. Now if you go back to sigma bonds, you can see this example where the two p orbitals approach each other horizontally and they merge together to produce one large cloud and two lone p orbitals. Here though, we can see that these two orbitals here are both merging together to produce this large one and this large orbital. And this dotted line is the internuclear axis, the line between two nuclei. As you can see, the pi bond has the orbitals above and below the internuclear axis. Now, usually a single bond is always a sigma bond, because we can memorize this with S and S. This is because there's no way a pi bond can form if you have, only one bond. For a double bond and triple bond though, the story is a little different. Here, for a double bond you have one sigma bond and one pi bond, and for a triple bond you have one sigma and two pi bonds. So watch here. We have two carbons, and as you can see we produce this carbon-carbon single bond. But for carbon-carbon double bonds, these two p orbitals have to come in to produce this carbon-carbon double bond. Now you may see that I highlighted these two orbitals in different colors. And that's because p orbitals are actually more like clouds that are above each other. Although there's two fragments, it still counts as one p orbital, so we should treat these like they're one p orbital, not two separate orbitals. So you can see the two of them merging together to produce this large carbon-carbon triple bond. Now the pi bond is structured in such a way that it does not interfere with the sigma bond, as you can see here. And there can only be one sigma bond in a covalent bond, because you can already see if there was more than one, well, I can't actually see how they're supposed to bond together. This, and then, yeah. There's only one s orbital, so there's no way two sigma bonds can occur at once between two of the same atoms. Now let's look at the so-called hybrid orbital model. Now we already saw that the Lewis structure is a great way to represent most atoms and molecules, actually most molecules. But we need this hybrid orbital model because the p orbitals are always arranged at 90-degree angles. And in the meantime, s orbitals are spherical. Except this creates some problems. A, it doesn't have any directionality. And two, it means that all covalent bonds are 90 degrees, which is very much false as seen from things like tetrahedrons. And also, some molecules can't be explained with the overlap model, like say methane. It's going to violate some of the rules. So that's why we made something called a hybrid orbital. The first one we're going to look at today is the sp3 hybrid orbital. As you can see, this is the outside orbital for carbon. So the 2s orbital and the 2p orbital for carbon. Now you can see that s has 2 electrons and p has 2 electrons, as it should be, because carbon's electron configuration is 1s2, 2s2, 2p2, because it has 6 electrons in total. However, these electrons can also merge to produce 4 sp3 hybrid orbitals. Because it's a hybrid orbital, it has properties between s and p, and that's the same for its energy level. Its energy level of an sp hybrid is always between that of an s orbital and a p orbital. So it has more energy than an s orbital, but less energy than a p orbital. sp3 bonds occur in carbon bonds, where it usually bonds to 4 hydrogens as seen here in tetrahedrons. An sp3 bond always occurs in tetrahedral molecules, such as methane, because it looks like a tetrahedron, as well as ammonia, water, and other molecules. The next one is the sp2 hybrid orbital. sp2 hybrid orbitals occur usually when carbon has a double bond to something else, usually an oxygen, like here in formaldehyde. Here, the 2 s electrons and 2 p electrons merge to produce only 3 sp2 orbitals and 1 lone p orbital. This extra p orbital, as long as one of these sp2 orbitals will go and bond with the oxygen atom, while these other 2 sp2 orbitals will bond with the hydrogens. The third orbital we're going to talk about is the sp orbital. The sp hybrid orbital is generally found when carbon has two double bonds, or 1 triple bond and 1 single bond, like here. If we merge 2 s orbitals and 2 p orbital electrons, then we can get 2 sp hybrid orbital electrons and 2 remaining p electrons. Now you see here, we have 2 p electrons because these 2 p electrons are going to form the double bond, because as you all know by now, pi bonds need a p electron to pair up. Also, this is true for triple bonds as well, like say in hydrogen cyanide. One of these sp hybrid orbitals will go here, because the sp will act like an s orbital and form a sigma bond. And these 3 electrons here will bond with the nitrogen, where the sp forms the first sigma bond and the other 2 p orbitals produce the double and triple bonds of the nitrogen. And I represented the structure of a carbon with an sp hybrid orbital present. And also, here's something I want to talk about. It's that for a particular molecular geometry, we can explain it using hybrid orbital theory. You can use that. But there's a problem. The reverse statement, that is, a specific hybrid orbital can be explained with molecular geometry, is false. Let me show you an example of this. We can say that water has an sp3 hybrid orbital because it has a 104-degree bend structure, like this. This angle is around 104 degrees, and that is about the 109.5 degrees which is expected for a tetrahedral structure. But a very similar molecule, hydrogen sulfide, or H2S, has a 90-degree angle, and you can't use hybridization to explain this. The overlap of the p orbital and s orbital is more than enough to explain the geometry of hydrogen sulfide, and therefore we don't even need to mention the fact that hybridization is used. And lastly, let's look at this chart. This chart explains the structure, the hybridized orbital, and bonding and non-bonding pair numbers. So take a moment to look at this and then study it. And here's the second one. So that was a lesson about hybrid orbitals, sigma and pi bonds. Thanks for watching and see you in our next AP Chemistry video. Bye!